There are three kinds of arrays that we've already talked about. The dynamic array, static array, and the string literal, which is a constant array. The dynamic array would look something like this. Our dynamic equals new char 10. So this will create 10 elements in heap that will be pointed at by the pointer rDynamic. A static array that functions very similarly would look like this. Char r static 10. And this will create 10 character elements in the stack. Then the string literal would look something like this. Char star r constant. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this will be a pointer that points at read-only memory. So I've already shown you that the dynamic array and the static array work in very similar ways in that you can access data elements. The constant array, the string literal, you can only read because the actual array data exists in read-only memory. You could also think about these three like this. Char star r1 equals r dynamic. This is just a regular old pointer pointing at memory. Char star const r2 equals r static is a pointer to memory, but you're not allowed to change where this pointer points to. It must always point at the specific spot in memory that it was initialized to when it was created. Const char star r3 equals r constant. And this right here is a pointer that points at constant characters. They're immutable. This code should all compile. Yep. If we want to see what these look like using our memory viewer, we can do that by simply changing where pointer points. So if I want to see the dynamic memory, I can use R1 right here. And this will show us the dynamic memory that was allocated. Here we're looking at 10 bytes. This is mark 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bytes here. And then there's these 4 elements there. But if we look to the left, to the data before the array, we have the same 4 elements there. These right here are actually sentinels. These formatted bits of memory show up in front and after our array that was allocated. Now these values are only really guaranteed to be there when you run in debug mode. They're not always there in release mode. Let me try running this in release mode and see if they're there. Control F5. Yeah, they still are. Those sentinel values are there to help a programmer discover if they're accidentally modifying data out of bounds. For example, if I were to do this, R1 -2 equals I, and then run this, that means -2 right there. If this is element 0, this is element -1, and this is element -2. Element -2 has that I there. And because this I is overriding a piece of the sentinel value, when I exit the program, nothing bad happened. Escape. Why did nothing bad happen? Oh, I know why. R1 is dynamically allocated. It isn't until it's deallocated at the end of the program or after use that the computer checks to see whether or not anything bad has happened to it. So if I do this at the end, delete R1, and now run it. So there's the I. If I press escape, there we go. That's what I was expecting. Heap corruption. Because I wrote into the sentinel value, and this will happen, by the way, in the same way if I write over here, it tells me that I have a heap corruption because the computer's looking out for me. It's actually a good thing that the computer crashes like this whenever there's an error with my programming. You want your computer to very loudly explain to you that you're doing something wrong, because the louder you can be told that you're doing something wrong, the better chance you have of fixing it. So we want our computer to be giving us these kinds of messages. So good compiler. So anyway, that's kind of what those sentinel values are there for. Let me get rid of this. But I do want to keep this delete. That's one of the key differences between a dynamic array allocation and any of these other array allocations. When you dynamically allocate something, you have to deallocate it. If you don't, then you'll create a memory leak, which can hinder your program and your computer as the program keeps running. So R1 is a pointer that points at dynamic memory. This right here was allocated in the heap, but R1 is actually a variable on the stack. And if I wanted to find that variable R1, if I wanted to see what that specific variable looks like, I would have to do something like this with my code. R1 is a pointer to a character, and when I apply the address of operator to it, I actually turn it into a pointer to a character. So this is going to resolve to a char star star. But I want it to fit into pointer, which is just a character pointer, so I typecast it to ease the compiler and tell it that it's okay and I know what I'm doing. So let's compile this and see what happens. So these 4 bytes are the pointer to dynamic memory. The current address here is 1EF9AC, and the value at this address is D33C0. Let's see what R2 would look like. I'm going to replace this with R2 and run that. And this takes me to the stack because R2 is the static array. R2 should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements here. And then it also has some sentinel values here. It has 1, 2, 3, 4 sentinel values, and then it should have 1, 2, 3, 4 more. But then it has these 2 extra. What's the deal with that? Oh, this has to do with something called memory alignment. So our static array is only 10 elements big. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But the computer prefers our bytes in groups of 4. Instead of allocating only 10 bytes for this array, it's actually faster and easier for the computer to allocate 12 bytes. And then after those 12 bytes, we have the 4 sentinel values for the array, and then 4 sentinel values for the variable just after this array, which it looks like a pointer, whatever this thing is. Whoa. Yeah. Pointer probably to heap. In fact, that pointer is probably R dynamic. And before this array should be this thing. What is this thing? This might be a pointer as well. This is also a magic number, the sentinel value right here. 0xCCCCCCCC is the value that Microsoft Visual Studio puts in memory to identify it as unused stack space. But anyway, this right here is probably a pointer. And this right here is probably a pointer. And I'm willing to bet that this pointer here is R constant, this pointer here is R dynamic, and this data in between is R static. I'd really like to be able to somehow traverse from this spot in memory and go into that spot. So I think I'm going to write some code that will enable me to do that. So down here in our switch statement, I'm going to add another, take caps lock off, another option. So when I press space, it will go in to whatever pointer our memory viewer is looking at. Int value at ptr. Well, first let me do this. Int star int ptr equals int star ptr. And then I'm going to dereference int pointer. And then this should be an address, which means I should be able to say ptr equals char star value at ptr. Alright, let's try that. Control F5. So let's find this pointer and press space. Yeah, look at that. It took me into the dynamic memory. Let me try that again. To here. Space. Yeah, look at, whoa. That's not what I was expecting. That's something else. Oh no, this is right. This is this static memory. Right there, there's 10 spaces. One, oh, and you can't tell the difference when I'm clicking on the gray when I'm marked. So let me change that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, oh, 10. Okay, let's try that. Space. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Cool. So now I can traverse through my memory. Let me see if I can find another thing that might be a pointer. Probably not around here. So I'm in read-only memory here, and read-only memory has a whole bunch of static constant data that is important to the program. We see all kinds of error messages that are stored in here. We see special kinds of constant strings that may be used by the compiler or by the program for whatever reason, for reasons that we'll probably never even see. So let me leave that and go to the heap. There's going to be a whole lot more pointers in the heap. Let's see if I can find another one. Like this. Yeah, here's one. So my current address is 2F3078, and this address here is 2F2FE8. And if you're trying this on your own computer, your hex values are probably going to be very different. That's because the operating system changes these values every single time you start your program. It's part of the virtual memory mapping that the operating system does for your program. Anyway, I'm pretty sure that this is a valid address because it looks very similar to my current address. I've written these programs enough that I can kind of spot a memory address. But I'm not actually guaranteed that this is a valid address, so I'm kind of gambling here. If I press space, it does happen to, ooh, look at that, cool stuff. It does happen to take me someplace. But if I were to try another piece of memory, like, what's this? So this block right here, 2F980D, I'm pretty sure this is not a valid memory address, because this is what a valid memory address does look like. Notice it starts with 2 zeros. This one starts with no zeros. That's usually a dead giveaway, at least in Windows, that a pointer is not valid if it doesn't start with a 0. But again, that could be different. That's just my experience. But if I try to go into this pointer using my handy dandy pointer traversal code, this happens. And this is exactly what I was expecting. I'm running this in release mode, so it just says it stopped working. If I run it in debug mode with just F5, let's find that pointer again. Actually, any pointer. Let's try to go into 0xCCC. Let's try to go to this memory location. If I press space, I get this unhandled exception in memory viewer access violation reading this location. It's telling me this because it tried to move the pointer to this spot, and then when it tried to access data at this spot, it realized it wasn't allowed to. So here, as it's trying to print the unique character at this location, it knows that it's a bad pointer, and Windows just flat out denies me access. This is a common thing that can happen in a program. This is called a segmentation fault. It's where you try to access memory that isn't really memory. Or when you look at a pointer and it actually isn't a pointer, it's just some arbitrary data that belongs to something else that is somehow being interpreted as a pointer. I should probably stop debugging. Stop.